So in the previous video, we discussed solving polynomial equations, and we talked about how whatever the degree is, that's how many total solutions you'll be getting. And right now, you have to be able to factor it down to linear and quadratic factors in order to get all of our solutions. Well, not all polynomials are factorable, so there are some problems that we won't be able to solve. However, we have an aid in something called the rational root theorem, which could potentially help us find zeros, but it's only going to be able to find the rational solutions, okay? So we're going to go over what's called the rational root theorem. And what the rational root theorem is it may aid in finding rational roots, zeros, solutions. So your solutions are when you're solving a polynomial equation, but remember, you're solving it when it's in standard form, so it's set equal to 0. When you have a polynomial function, right, just f of x equals a polynomial, the zeros of the function are the values of x that will output 0. And roots are the same thing, the values of x that give you an output of 0. So that's why roots, zero solutions, when you're solving, it's just when it's set equal to 0. Of a polynomial with integer coefficients. So if the polynomial doesn't have integer coefficients, we can't use the rational root theorem. So what the rational root theorem does is it generates a list of all of the possible rational roots. Okay, that doesn't necessarily mean that these are all of the roots that there are, but just if the polynomial has rational roots, it'll be in this list. Okay, and so the rational root theorem, okay, states that if a polynomial function has rational roots, they will be of the form p over q. P is a factor of the constant term of the polynomial, and q is a factor of the leading term. So you might want to pause the video, make sure you have all of this written down. Okay, so the rational root theorem allows us to generate a list of all possible rational zeros. Then, if a polynomial has a rational zero, it must be in this list. So it allows us, we can always find rational zeros. Now, not all polynomials have rational solutions, so this wouldn't help us if all of the solutions for a polynomial were not rational, okay? Were either irrational or imaginary. But if a polynomial has rational solutions, rational roots, they will be in this list that we can generate. So we're going to practice right now generating that list, okay? So make sure you have all of this down. So number 1 says we're going to list all of the possible rational zeros of f of x. So if you notice, f of x is a 5th degree polynomial. It has 5 total zeros. We don't know how many of them are rational, if any at all, but we can generate a list of all possible rational zeros, which means if f of x has a rational zero in it, it's going to be in this list. And what that means is that if I plug it in, it's going to give me an output that is 0. So to generate the list, we do p over q. P is every factor of the constant term. So the constant term is 16. So we're going to list all of the factors of 16. So 1, plus or minus 1, plus or minus 2. You have to include the negatives. After 2, then 4. After 4, 8. After 8, 16. So these are all the factors of the constant term. Now, all of the factors of the leading term. So you have to make sure you're in standard form. Okay, so now we can generate our list. Okay, it's going to be every factor of the numerator over every factor of the denominator. Every factor of p over every factor of q. So we've got a pretty big list here. So what we do is we take each p and put it over each q. So plus or minus 1 over plus or minus 1, that's just going to be plus or minus 1. Plus or minus 1 over plus or minus 2, that's going to be plus or minus 1/2. Plus or minus 1 over plus or minus 4, it's going to be plus or minus a fourth. Then plus or minus 2 over plus or minus 1, that's going to be plus or minus 2. Then plus or minus 2 over plus or minus 2, 2 over 2, that's just going to be plus or minus 1, so we don't need to write it again. And then plus or minus 2 over plus or minus 4, 2 over 4, we don't need to write it again, we have 1/2. So move on, plus or minus 4 over plus or minus 1, so that's new additions, okay? Then we have plus or minus 4 over plus or minus 2, that's just going to be plus or minus 2, so we don't need to list it again. This over this is going to be the same as this, so we don't have to list it again. Now move on. This over this, that's new. Okay, this over this, not new. Plus or minus 4, right? This over this, plus or minus 2, not new. This over this, that's new. And I don't think we're going to have anything else that's new, right? That's going to give me 8, that's going to give me 4. So, if this function, if this polynomial f of x has any rational zeros, meaning values of x that output 0, it has to be in this list, okay? Now, all 5 of the solutions, or all 5 of these zeros, might not be rational at all. But if any of them are rational, they are sitting in this list. So what you would do is, you would plug them in. You would plug 1 in and see if you output 0. If you output 0, then 1 is a rational 0. So you found one of the solutions. Okay, and number 2 it says, find all of the zeros of this function, f of x equals, and we have a 4th degree polynomial. So if it's a 4th degree, that means there are 4 total zeros or 4 total solutions, because solutions are going to be the values of x, right? When you're in standard form, you have an equation. So taking this and setting equal to 0, okay, means you now have your equation. So notice, how would I find the zeros? I would try and factor this to get all 4 of my zeros. But this isn't factorable. So we hope that this has some rational zeros, because if it does, we'll be able to identify them, because we're going to generate a list of all of the possible rational zeros. So first step is I try and factor this to find my zeros. I can't. Okay, so now I'm going to see, hopefully this function has some rational solutions. So we make a list, right? Plus or minus all of the factors of the constant term. So it's going to be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15 over all the factors of the leading coefficient, the leading term, coefficient on the leading term, right, which is 4, so plus or minus 1, plus or minus 2, plus or minus 4. So we make our list. That's going to be plus or minus 1 over plus or minus 1/2 over plus or minus 1/4, then 3 over 1, so plus or minus 3, 3 over 2, that's new, plus or minus 3/2, that's new, plus or minus 3/4, then plus or minus 5, then plus or minus 5/2, then plus or minus 5/4, long list, then plus or minus 15, then plus or minus 15 over 2, then plus or minus 15 over 4. None of these are the same. So, if this function has any rational zeros, it is in this list. So, what we start doing is, we start plugging all of these rational zeros in. So I start by plugging in, all of these values, we plug them in. So I start by plugging in 1. So 4 times 1 to the 4th minus 12 times 1 to the 3rd plus 25 times 1 squared minus 14 times 1 minus 15. I'm going to see what that gives me. Okay, so we can put it right into the calculator. And it's going to give us a value of negative 12. So is positive 1 a zero of this function? No. When you input 1 for x, you do not output 0, you output negative 12. So 1 does not work. So now we'll try negative 1. Okay, so we'll put that into the calculator, and we'll see what it gives us. It gives us 40. So is negative 1 a solution? No, it is not. So now, let's move on. Let's check to the next one in our list. The next one in our list is a half. So 4 times 1/2 to the 4th minus 12 times 1/2 to the 3rd plus 25 times 1/2 squared minus 14 times 1/2 minus 15. That gives us, let's see, 4th. That gives us negative 17. So is positive 1/2 a root? No, it is not. So we keep going through our list. Now we'll do negative 1/2. Okay, so now let's go through and check. Whoop, I read to the third there. And this gives us 0. So finally, we found a root. One of the values of x that make this output 0 is negative 1/2. Okay? So what that means is we know, okay, keep doing your work below this. I just ran out of room. So we know that one of the solutions is negative 1/2. Which means if one of the solutions is negative 1/2, that means that one of the factors must be x plus 1/2. So we know we can take f of x and write it as x plus 1/2 times something. Now we have options here, okay? We have options. What we can do is we can keep going through our list of rational zeros and see if this has any more rational zeros, okay? Because if this has any more rational zeros, they're going to be in this list. Or what we can do is we can say, okay, this is a linear factor, okay? If I divide it out, I can get my third degree here. And my third degree, I might actually be able to factor it, so it might be less work than plugging all of these in. Okay, so I'm going to you could if you wanted to. You could go through all of these and see if you get any more rational zeros. And if you do, then you know more of the factors and you know some of the solutions. But what would I do right now? Okay, I could get this third degree by dividing out x plus 1/2. So that means I would put negative 1/2 in the box. I don't need any placeholder, so it'd be 4, negative 12, 25, negative 14, minus 15. Okay, bring down 4. 4 times negative 1/2 is negative 2. Negative 12 plus negative 2 is negative 14. Negative 14 times negative 1/2 is going to be positive 7. Okay, that's going to give us 32. Half of 32 is negative 16. Add that column, we get negative 30. Negative 30 times negative 1/2 is 15. We add that up and we get 0. That's going to give us constant, linear, quadratic, cubic term. So 4x to the third minus 14x squared plus 32x minus 30. Okay? And now we know this already gave us this solution of negative 1/2. Now, look at what we have. Our 3 remaining come from this polynomial right here. Okay? So, notice, if I try and factor that, I can't factor it. So I would be in trouble. So what that means is, okay, I can't factor this. So I have one of my answers, okay? So what this means is I'm going to have to go back through this list, okay, and see if any of them make the output 0. Otherwise, I can't find any more solutions. So I'm going to go through my list. I'm going to keep going, okay? Next I would do is I would plug in a fourth, negative 1/4. I'm going to tell you right now they wouldn't work. 3, negative 3, they wouldn't work. Positive 3/2. If you plug in positive 3/2, you are going to get 0. So we find another, okay, you go through your list and 3/2 is going to work. So what that means is another factor is going to be, if 3/2 is a root, then x minus 3/2 is a factor, which means, okay, I factored out, once I got one solution, I wrote out its factor. So now I know another solution. So where do I take this factor from? This factor I'm going to divide from this polynomial, okay? I factored out the x plus 1/2, so it knocked this 4th degree down to a 3rd degree. So if I factor out another linear factor, I should get a quadratic here, okay? So now I have to do synthetic division again. 3/2 goes in the box. I don't need any placeholders. I'm in standard form. 4, -14, 32, -30. Drop down the 4. 4 times 3/2, that's 12/2, that's 6. -14 plus 6, that's -8. -8 times 3/2, that's -24/2, that's -12. Add that up, that's 20. 20 times 3/2 is 60/2, which is +30. Okay, this is what we expect to get here, that's 0, right? So this would be 4x squared minus 8x plus 20. So, find all of the zeros. There are 4 of them, right? We found the rational ones using the rational root theorem. The other 2, look, this, I could take out a greatest common factor here, okay? However, there's nothing else I could take out that will let me use the AC method here. So the only way, notice I have 2 more zeros, but they aren't going to be found by factoring. I have a quadratic, and we know how to solve all quadratics. So I set this equal to 0, okay? So -8 plus or minus the square root of -8 squared minus 4 times 4 times 20 all over 2 times 4. -8 is 8. Okay, 2 times 4 is 8, so we got to get the value of the discriminant. So it's going to be -256, okay? And it's imaginary, so look, the last 2 zeros are actually imaginary. Okay, the square root of -256, you need to simplify that. That's 16i. So this is going to be 8 plus 16i over 8, and then 8 minus 16i over 8. That's going to be 1 plus 2i, and then that's going to be 1 minus 2i. So this, all of the zeros, there are 4 zeros. We have -1/2, we have 3/2, and then we have 1 plus or minus 2i. Those are your 4 zeros. So just reviewing what we just did, okay? You try and factor. I can't factor. So you make your list of possible rational zeros, okay? Once you hit 1, that's really good. That means you found one of them. You should try and factor this, okay? Factor it down. See if this is factorable. It's not, so keep going through your list and hoping, okay, and trying to find another rational zero. We found a rational 0, 3/2, so we knew one of the factors, another factor, had to be x minus 3/2, so now we could divide that out. And so now we got this down to a 2nd degree right here, which it's okay if we can't factor this anymore because we know how to solve all quadratic equations. Okay, so we'll do one more problem. Okay, so in our last problem, it says we're supposed to solve the polynomial equation x to the 3rd plus 10x squared plus 31x plus 30 equals 0. So the first thing that we would try, okay, first we check it's in standard form of a polynomial equation. That's good. Check to see what the degree is. The degree is 3. That means this has 3 total solutions. First thing we should do, 4 terms, we should try and factor this. Factor by grouping is not going to work here. So what that means is we can't solve and get our 3 solutions by factoring. So what we should try and do is use the rational root theorem. Hopefully one of the solutions, at least one of the solutions, is rational, because if it is, we're about to find it. So we generate our list of possible rational zeros. So all of the factors of the constant term over all of the factors of the leading coefficient. Now remember, you can only use the rational root theorem when you have integer coefficients. So if this said 5, 6, we wouldn't be able to use it until we had all integer coefficients, okay? So all the factors of 30, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30, over, okay, just plus or minus 1. So our list is going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. Okay, so we start going through, go through 1 first. So 1 to the third, plus 10 times 1 to the second, plus 31 times 1, plus 30. Okay, if you notice, these are all positive, so we know this can't equal 0. Negative 1 to the third, plus 10 times negative 1 squared, plus 31 times negative 1, plus 30. This is going to be negative 1 plus 10 minus 31 plus 30. Okay, this is 9 minus 1. This is 8, so that doesn't work. Okay, plug in 2. Look at this. Does 2 even make sense? If I plug in 2, can I output 0? No. Do any of these positive ones really make sense here? No. So I'm just going to check. Next, I'm going to check negative 2. So negative 2 to the third, plus 10 times negative 2 squared, plus 31 times negative 2, plus 30. That's going to give me negative 8, okay? That's 4 plus 4 times 10, that's going to be plus 40. Okay, this is going to be minus 62, right, plus 30. So that's going to give us negative 8 plus 40 minus 62 plus 3 puts us at negative 27. That doesn't work. Okay, I'm going to plug in negative 3. So that's negative 3 to the third plus 10 times negative 3 squared plus 31 times negative 3 plus 30. Put that into your calculator. Let's see what we get. Ooh, we got 0. So we found a value that's a solution. One of the solutions is negative 3. So if I know what one of the solutions is, that means I know what one of the factors is. If negative 3 is a solution, then x plus 3 is a factor. So what this means is, okay, this was a third degree. I now have a linear factor, which means all I need to find is this quadratic factor. Could one of the solutions hidden in this factor be rational? Yeah. Could both of them be rational? Yeah. Could none of them be rational? Yeah. But this is a quadratic, so will you know how to solve whatever you put here? Yes. So instead of going through this list anymore, we should factor, okay, write this in its factored form, which we can now using synthetic division. 1, 10, 31, 30. We don't need any placeholders here. Bring down the 1. That puts us at 10 plus negative 3, which is 7. That puts us at negative 21. That gives us 10, negative 30, 0. So this is x squared plus 7x plus 10. Can you factor that? No. So we know this isn't going to have any integer solutions left. And now, since this is a quadratic, you know how to solve all quadratics. You can use a quadratic formula. You could complete the square if you wanted to, too. So this will be negative 7 plus or minus the square root of some value over 2. Okay, let's get the value of the discriminant. All right. Whoa, I'm sorry. X squared plus 7x plus 10. That is factorable. We didn't even need to use the quadratic formula. This is going to be 9. I apologize. This is going to be negative 7 plus 3 over 2. This is going to be negative 7 minus 3 over 2. You will have it. This is negative 4 over 2. This is negative 10 over 2. You get negative 5 and you get negative 2. I apologize. Both of your solutions will be rational. Okay, will be integers. So, yeah, you could factor that, right? What two numbers multiply together give you 10 and add together give you 7. So if you had just went through this entire list, this time you would have found all three. But that's not always going to happen. So the solutions here are -3, -2, -5. Okay? Just work with what you have, and the rational root theorem helps you to find, okay, rational zeros. Not all zeros, just if your polynomial has rational solutions, has rational zeros, they will be in this list. Okay? So when you are solving, if you try and solve and you can't because it's not factorable, you should be trying the rational root theorem for possible rational zeros. Then, if you didn't have any rational zeros, then you wouldn't be able to go any further. Okay? You wouldn't be able to find any of the irrational or imaginary zeros. An alternate way of trying to find solutions when you can't find them by factoring is actually looking at the graph, okay? And when you look at the graph, what are the values of x that output 0? Those are going to be your x-intercepts. So you can see if you have irrational values by looking at a graph, okay? But you're not going to be able to get them algebraically through factoring. So that's it for rational root theorem.